t to the power n plus r minus 1. Now, in place of f here, I have PDF of d1, d2, dn minus 1 was nothing but g of d1 by sigma, g of dn minus 1 by sigma. So, g of t d1, t dn minus 1. So, if you are writing down everything in terms of random variable, it should be t d1, t d2, t dn minus 1, dt. So, just reproducing the formula from the scale family, 0 to infinity t to the power n plus twice r minus 1, g of t d1, t dn minus 1, dt. Right. So, this is what, and what is your g? Where g of d1, d2, dn minus 1 was nothing but, yeah, minus infinity to infinity. So, sigma I have taken to be 1, right. So, 1 by g of d1 by sigma plus t dn minus 1, the sigma is 1. So, dn minus 1 plus t dt is what you get. Right. So, that was all about estimation of a sigma. One can similarly consider estimation of mu, but before I go to estimation of mu, let me just do one quick example. Suppose x1, x2, xn are IID, normal mu sigma square. Theta is mu sigma square, which belongs to capital theta, which is r cross 0 to infinity. Suppose I consider estimation of sigma to the power r. Now, if mu was known, I considered this problem in the last lecture, if mu was known, and I had taken there mu to be 0. Okay. So, what I need to do over here, and my loss function, suppose a by sigma to the power r minus 1 whole square. So, one way is I apply this formula, which is going to be slightly complicated, because first I have to get sorry, I made a mistake over here. This would not be the same d. This is coming from f, right? If you recall, this is f of the original f, d1 plus dt, dn minus 1 plus t, and t dt. Right? You got the joint PDF of d1, d2, dn minus 1 and xn, and then you integrated out the variable corresponding to xn to get the joint PDF of d1, d2, dn minus 1. So, this is what exactly you got. So, one way is you directly apply this formula. In fact, it is not going to be difficult, because this all you know is normal and everything. But I can make things much simpler. What I do is I try to find out one estimator of sigma to the power r, which is invariant. Now, note that sigma square can be estimated by summation xi minus x bar whole square. So, I choose my delta naught x xi minus x bar whole square. So, this was for sigma square. So, sigma to the power r would be nothing but this to the power r by 2. first thing I have to see whether this belongs to di or not. So what I do? I have to apply bx1 plus c, bx2 plus c, bxn plus c. If I apply over here, so that means bxi plus c. If I apply bxi plus c in all the observations, x bar gets transformed to bx bar plus c. cc gets cancelled, b becomes common. So it becomes b square xi minus x bar whole square. B square when comes outside, it becomes b to power r. So what you get is delta naught of bx1 plus c, bxn plus c turns out to be b to power r times delta naught of. And that is what exactly the definition of invariant decision rule was in this situation. So this implies that delta naught belongs to Ti. Now in this case, we know that what is a complete sufficient statistic? X bar and summation xi square. Or equivalently, x bar and summation xi minus x bar whole square. And this is a function of summation xi minus x bar whole square. So this is a function of complete sufficient statistic. Now, that means this conditional expectation is going to same as unconditional expectation. So what do you get? The MRI. So MRI is delta star x, which is expected value of under mu is equal to 0 and variance 1 of delta naught x E01 delta naught square given x into delta naught x. Now note that summation xi minus x bar whole square is chi square on n minus 1. So that means delta naught x is nothing but chi square n minus 1 to power r by 2. So this is same as E01 expected value of chi square on n minus 1, because under mu is equal to 0 and variance 1, summation xi minus x bar whole square is chi square on n minus 1. So E0 chi square on n minus 1 divided by r by 2 divided by expected value of delta naught square. Delta naught square makes it summation xi minus x bar whole square to power r. Summation xi minus x bar whole square is chi square on n minus 1. And then delta naught x, which is nothing but summation I is equal to 1 to n. So you see similar kind of a thing we saw when mu was known, except that over there you got summation xi square, which was chi square on n. So you got here x blue chi square n to power r by 2. So everything same with n minus 1 getting replaced by n, and here you got summation xi minus x bar whole square. So exactly the same thing. Now one can get MRI directly from this formula. Let me just do that over here. Now these values you can calculate, which would be in terms of gamma functions. So one could have gotten this directly from. So first let's try to see what is a g of d1, d2, dn minus 1. In fact, this is a joint PDF of d1, d2, dn minus 1. If you try to look at other way to look at it, it would be joint PDF of d1, d2, dn minus 1, which is x1 minus xn, xn minus 1 minus xn. Now, this is certainly has multivariate normal distribution, because to show that this has a multivariate normal distribution, what I need to show? That linear combination of all the components is univariate normal. So if I consider any linear combination of x1 minus xn, xn minus 1 minus xn, that means c1 times x1 minus xn and cn minus 1 times xn minus 1 minus xn, that would be some linear combination of x1, x2, xn only. But x1, x2, xn are IID normal. So their linear combination would have a univariate normal. So that means any linear combination of these components is univariate normal, which says that it would have a multivariate normal. Now, if it has a multivariate normal, what would be the parameters? In the case of multivariate normal distribution, I know the parameters are the mean and variances. So what is the mean vector? x1 and xn are IID, so mean x1 minus xn is 0. So for each of them, mean is 0. Similarly, xn minus 1 minus xn, each of them has a mean mu. So mean of xn minus 1 minus xn is 0. And then you have a variance covariance matrix. x1 minus xn has a variance twice sigma square, because they are independent, so variance of x1 plus variance of xn, 2 sigma square. What is the covariance between x1 minus xn and x2 minus xn? Everything would get cancelled and only thing would be left with, so covariance of x1 minus xn and x2 minus xn would be nothing but covariance of x1, x2 would be 0, because x1, x2 are independent, covariance of x1, xn is 0, covariance of xn, x2 is 0, and then get plus plus, which is nothing but variance of xn, which is sigma square. So it would be sigma square, sigma square, sigma square, sigma square, twice sigma square, sigma square, sigma square, sigma square, sigma square, sigma square. So joint PDF of d1, d2, dn minus 1 would be this quantity. Right? So exactly you know what would be the joint PDF of d1, d2, dn minus 1. You can write down this as this. Slight more complicated computations, but finally you will exactly get the same thing through various transformations and so on. So if you want to do some adventure, I would suggest that plug in it over here, and then finally you should get this answer. So, so this was about the estimation of sigma to power r when you have a affine group of transformation in the location scale family. So in the following lecture, I'll deal with estimation of mu and see what will be the minimum risk invariant estimator. Just let me conclude this lecture with the fact that one can directly, although in this case I reduce first problem from location scale to scale, and then I saw that I don't have to do anything, all the results of scale family can be used over here. One thing one should note over here, that here G bar acts transitively on parameter space. So for that, what I have to show is let mu1 sigma 1 and mu2 sigma 2, they belong to theta. Then what I have to show? I have to show that mu1 sigma is related to mu2 sigma 2 through the relation b mu1 plus c and b sigma kind of a thing. So that is not difficult to see, because mu1 sigma 1. So first of all, sigma 1 should be related to sigma 2 through some b. So first I determine that, so that b is determined. So this can be written as, yeah, sigma 1 by sigma 2 into sigma 2. So that means my b is sigma 1 by sigma 2. So I should be write down this as b sigma 1 by sigma 2 of mu 2, right? Because it will be b mu 2, and then c can be mu 1. So now actually I can write down more clearly. This is same as sigma 1 by sigma 2 mu 2 plus mu 1 minus sigma 1 by sigma 2 mu 2. this could be C. And then sigma 1 by sigma 2, sigma 2. So I took the same B over here because it will be. So this is nothing but B mu 2 plus C and B sigma 2, which is nothing but G bar BC of mu 2 and sigma 2. So that means any two parametric points are related through the transformation G bar BC. So what does that suggest? That suggests that G bar acts and as a consequence of that, you can say that risk of any invariant estimator is constant. So let me conclude this lecture with few comments. Note that all the three models which I am considering over here, location model, scale model, and location scale model. In all the three cases, G bar acts transitively. But that may not be always the case, as you'll see through some of the problems in the assignment. So in those situations, G bar does not act transitively on theta, so the risk of any invariant estimator is not constant. So then, in those situations, finding the minimum risk invariant estimator again may be a difficult task. Or it may not exist because then you have to minimize the risk function at every parametric point theta. And that was the whole problem, that you're not able to minimize the function at every theta. When G bar acts transitively, risk of an invariant estimator is constant, then you are able to find an estimator for which this constant risk is minimum. So there would be situations, as you will see in the assignment, where G bar does not act transitively on the parametric space. So that suggests that in those situations, the minimum risk invariant estimator will not be possible. So you can eliminate some invariant estimators which are inadmissible, but as such finding minimum risk estimator may not be possible. Second thing is, here I did not use directly that G bar acts transitively on theta, rather I used it indirectly. In the sense that first I reduced my problem of estimating sigma 2 power r to the only scale probability model, which was through that PDF G of d1 by sigma and dn minus 1 by c. And then just I used the results of the scale probability model to get the desired minimum risk invariant estimator. So that's all for this lecture. So in next lecture, I'll deal with estimation of mu in the location scale probability models under the affine group of transformations. Thank you for your patience and thank you very much.